All right, so this presentation was given as part of a workshop in SOF 2025, and that workshop was Forensic Toxicology Validation, Navigating the Latest ANSI ASB 036 Revisions, and that was the part two of a two parts workshop on method development and validation. And so yeah, I thought I'd record a version of this presentation and put it up here online for you to enjoy. Enjoy might be a strong word, but anyways. All right. Okay, so no disclaimer. So first thing, let's talk about what qualitative methods are and methods that are types of methods that are closely associated with qualitative methods. So qualitative methods, of course, they're in opposition to quantitative methods. A qualitative method is one that yields a binary result. In other words, the result will always be one of two things. So your result can be positive or negative. So that's a qualitative method. With qualitative identification methods, the substance will be detected or not detected. Color tests would be a classic example here. With qualitative decision point methods, the analyte will be classified as being above or below a predetermined cutoff concentration. Something typical would be an instrumental method that is designed for a per se limit. So for example, we analyze a 10 microgram per ml GHB control by LCMS, and we can tell whether unknown samples are above or below this level. Okay, screening methods. Screening methods are often confused for qualitative methods, but they're not the same thing. Screening methods, they're a cousin of qualitative methods, really. Qualitative and quantitative relate to the form a result takes. Is it a word or is it a number? Screening relates to the quality of a result and its place in the workflow. So a screening method yields a preliminary result. We're typically referring to a quick, cheap method with some interferences. It's quote unquote, lower quality is reflected by the lower number of identification points granted within ASB 113. For a definitive reportable result, this needs to be followed by a higher quality confirmation method, and that generally garners a higher number of points. So why do we still use screening methods? Well, because they remain useful to direct the workflow. If you have a series of confirmation methods available, your screening result might guide you in choosing the proper confirmation. Okay, so both types of methods, qualitative and screening, they appear in the first and current edition of ASB 036, so the standard practices for method validation in forensic toxicology. Estimation of the LOD and validation of the processed sample stability, they're required for all of them. When screening with immunoassay, you also need to look at the precision at the decision point. When screening with other methods, you need to evaluate interferences from the matrix, from other analytes, and ionization suppression enhancement for LCMS methods only, of course. And to validate qualitative methods, you should, on top of all that, look at carryover. So you might wonder why the differences between the three types of methods, and really, I have no idea. Okay, so what about the second NCASB 036 edition? Well, as it relates to non-quantitative methods, there are two major changes. First, the notion of screening methods is abandoned entirely. The only option you have is a qualitative method. Second, to the validation parameters that were laid out in the first edition, we add one big one, the estimation of the number of false results. For the remainder of this presentation, we will discuss these changes in more detail. But not too much detail though, because the new edition isn't out for public comment yet, and so I cannot go into specifics like the number of sample required and such. But what I can do is discuss the existing literature, recommendations on qualitative method validation, which to no surprise is not going to be very far from the requirements because that's what we relied on as a working group to draft the second edition. Um, so yeah, the requirements will be made clear when the document comes out for public comment, of course, and this is supposed to be, oh wait, 5 years ago. I'm only barely joking. But yeah, there are like 1,000 level of approval for these, so it's quite a lengthy process. Okay, so let's go back to the first big change, which is the disappearance of screening from the document. For those of you going like, what now? I'm not allowed to do screening. Are you crazy? Well, no, of course you can still do screening. That's entirely your decision. ASB 036 just kicks this consideration out of its purview. ASB 113 already deals with this by giving a lower number of points to typical screening methods. ASB 036 second edition says, whatever its place in the workflow, all qualitative methods must be validated the same way. Its role in the workflow is irrelevant. So it's irrelevant as long as you use it to contribute points to the ID. If hypothetically you want to have something that's out of scope, not validated according to guidelines, not contributing points to the ID, but really just directs the workflow, be my guest. As far as ASB is concerned, this tree falls in a forest where no one hears it. That said, I'm going to say that the zeitgeist in laboratories throughout the world right now is doing away with screening. Democratization of highly specific methods like LCMS really allow that. All right then. Okay. One for all and all for one. It's all about qualitative methods. So how do we validate those? Well, let's go back to basics. Why do we validate methods? We want to demonstrate fitness for purpose. Well, what is the purpose of qualitative methods? Well, that's the first thing we covered, right? Their purpose is to classify samples into one of two categories, like positive and negative. Well, we measure whether this is well done by tallying up the number of true and false results, right? This gives us information about the probability of a mischaracterized result in qualitative methods. I will work with positives and negatives here, but this applies equally well to above, below threshold, and detected, not detected. You get the gist. It's one of two things. So to help us understand this validation step of looking at the false, positive and negative results, we need to understand a bit better how qualitative methods work, their theoretical behavior. Okay, well, a good way to visualize the performance of the method is by plotting the percent positive samples versus the concentration. So this here would be a perfect qualitative method. All samples with a concentration below the LOD or cutoff, they score negative or not detected or below cutoff. And all of the samples with a concentration higher than the LOD or cutoff, they score positive. So there are no false positives, no false negatives, right? That's a dream. But of course, we know it's going to be more of a mixed bag, especially close to the threshold. Because, I mean, yeah, if we analyze 100 blank samples with a concentration of 0, I sure hope they all turn up negative, bearing any interferences. And if we analyze 100 samples with a concentration super high, 100 times the cutoff concentration, it shouldn't be a challenge to say, yep, they're all positive. But what happens if we analyze 100 samples at exactly the cutoff concentration? Well, the signals are all going to be a bit different just due to the random error. It's probably going to look something like this. And 50% of those will be positive, 50% will be negative. Well, what happens if I'm right below the cutoff in terms of concentration? So the signal drops on average, but we still have this distribution, this variability of the signals, and some of them are going to score positive even if they're not. These are false positives. Of course, as we move away and away and again away from the threshold, we get a smaller number of false positives until we can reliably classify all of the samples as negative because our concentration is far away from the cutoff signal so that there's no overlap of the distribution with the cutoff signal. Well, a similar thing, of course, happens above the cutoff, but this time we're dealing with false negatives. And as we increase in concentration, their number go down, 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 and down until we can reliably classify all of the samples as positives. So what does this mean? Well, it means the positivity graph will look not like this, but it will look something like this. And if at this point you're thinking, well, okay, it doesn't work at 10 nanogram per ml, but it sure looks like it works at 20 nanograms per ml. So I'm just going to put my cutoff at 20 and it's all going to be good. Nope. This is what you get with a cutoff at 20 nanograms per milliliter and a cutoff at 30 nanograms per milliliter and at 40 nanograms per milliliter. So you're starting to understand this is an intrinsic property of qualitative methods. A zone of unreliability exists. Nobody would say for a quantitative method, I've had such a great idea. Let's just move things around so we don't have this pesky measurement uncertainty anymore. No, it's always going to be there. It can be managed, it can be reduced, but it can never go away. And the same goes for the unreliability zone of qualitative methods. It's there. We need to deal with it. Okay, so how do we deal with it? Well, basically, you get out of its way. You measure how large it is, and you validate right outside of it. That's it. Okay, so we need to validate right outside of it, and so we need to know what the limits of this unreliability zone are. So how do we estimate the reliability limits? We do that in the development stage. Okay, so let's estimate the size of the unreliability zone. So the reason why we suggest or mandate in ASBO 36 second edition that this be part of the development is because, well, if you reach validation and you just put random values for the unreliability zone, and then you go, holy moly, the unreliability zone that I used is way too small and my validation failed. well, you're sort of right back to square one. We don't want that. Or if you go, wait, the unreliability zone that I now learn about in validation is way too big for my client. Again, you're back to square one of developing your method, and we don't want that. So, needs to be done at the development stage, and there are a few approaches to do that. So, the first one is what I call an executive decision, aka, whatever, let's just say it's plus or minus 50%. So it's like whatever you're using this method for, you have no interest in having a particularly small unreliability zone. So you go for an arbitrarily large one, but not insanely large either. Large, but you can live with it. At the development stage, you can spike 10 samples at 50% above the cutoff for LOD, and you check that all of these samples are correctly classified as positive. You shouldn't have more than one sample failing, really, that sort of test. And you do the same at 50% below the cutoff and check that they all turn up negative. If they're all A-OK, you're good to go to validation. If this simple check doesn't work, I would be worried about going forward with a method that has an uncertainty zone of more than 50%. And actually, as we'll see later, it's forbidden by ASBO 36 second edition, and for good reason, because more than 50% of an unreliability zone is really getting on the large side. So maybe try and shrink that down the way you would reduce measurement uncertainty. All right. To be honest, my initial reaction to this approach was, wow, this is so lazy. I mean, what? We can't be bothered to look into things more deeply? You take sort of the easy way out of an executive decision, because there are at least two other methods you could use. First, we can use the experimental route, a bit like you would spike and analyze samples of decreasing concentrations to estimate the LOD. Well, you could spike samples at different concentrations around your threshold and analyze them to see if they get correctly classified or not. Mind you, if you want to estimate the proportion of false results at these different concentrations, you need at least 10 replicates for each level to get somewhere, and we'll get back to that later. But that's kind of experimentally intensive, right? Probably 3 concentrations above, 3 concentrations below, times 10 replicates. We're already at 60 samples minimum, and we don't have such a precise estimation of the unreliability zone. It's already better than the executive decision for sure, but isn't there a better way? Um, well, what if we rely on the theory of signals in analytical chemistry? We might just be able to calculate our way out of this. We've already said as much today. Spike 100 samples at the cutoff concentration, and you will get tiny differences in the measured signal just due to random error. Typically, we'll get a normal distribution of signals. Okay, so let's assume that the standard deviation of the signals remains stable. The question then becomes, when I move this distribution away from the threshold, when do I get to a point where I am classifying less than 10% or 5% or 1% or whatever percent of the results I choose incorrectly? Well, the answer to this is the mean plus or minus standard deviation S times t, which is the t-value associated to the desired false result percentage. But this is a value in signal units that you get. For it to be useful to us, we need to convert it to a concentration value. Well, generally, when we want to convert a signal to a concentration, we use calibration curves, something we don't have here. But we can do a 1-point calibration, aka a rule of 3. Well, this might all be a bit clearer if I show you how this would work with an example. So let's say I'm developing a qualitative method for a new drug. It has a decision point of 50 nanograms per liter. I want to estimate the size of the unreliability zone prior to validation. Okay, so I prepare 10 samples spiked at the decision point, 15 nanograms per ml, and I analyze them. I get these signals here with a mean of 5.61 and a standard deviation of 1.15. Okay, let's calculate the limits of my unreliability zone. What t-value shall I use? I want a false result rate of 5%. All right, and I use 10 replicates to estimate my standard deviation. So degrees of freedom is 10 minus 1 equals 9, meaning if I go into the different tables or if I use the software to give me this value, associated value with this alpha and this degrees of freedom is 1.833. Okay. So if I do the calculation, my unreliability zone runs from 3.5 to 7.72 in signal units. Okay. Okay, well, I need to convert it to concentration units. So to do that, I'll use a simple rule of 3 with the decision point, signals times 15 nanograms per ml divided by 5.61. And my unreliability zone is therefore 31.2 to 68.8 nanograms per milliliter. So pretty neat, right? But what's that saying again? If you want to make God laugh, tell him your beautiful methodology and he will mess that up. Turns out there are two complicating factors, at least in LCMS methods. First, when I presented the calculation approach, I very casually said, let's assume the standard deviation of the signal is stable. Well, guess what? Of course it isn't. It typically varies with concentration. That's something that's called heteroscedasticity, and it's a well-known phenomenon in analytical chemistry. That's why we use weights on our calibration curves, for example. But what was surprising to me was how this phenomenon occurred or showed up even over narrow concentration ranges surrounding the threshold. Okay, well, that complexifies the calculation, but we can still get through this. I'm not going to show the detail today, but it's doable if we wanted to get around this just by calculations. But then comes the coup de grace. Instrumental sensitivity varies from day to day in this type of instrument. Of course it does, right? Otherwise, why would you bother running one calibration curve per batch? You could run one when the method gets validated, and then you would be good to go forever. But no, sensitivity varies daily. What you might not have appreciated is this means the size of the unreliability zone varies daily, therefore. Yeah. So now is the time I wish I could swear. So this one I found no way around, to be honest, which is why I'm saying, well, executive decision doesn't look like such a dumb option now, does it? In any event, whatever approach you settle on to estimate the size of your unreliability zone, ASBO 36 second edition mandates that the lower limit be greater or equal than 50% of the decision point or LOD concentration. And, by symmetry, upper limit should be at 150% or lower of the decision point. So what this means is, for example, if my decision point is 100 nanograms per ml, well, the lower limit should be somewhere between 50 and 100 nanograms per ml, and by symmetry, upper limit should be somewhere between 100 and 150 nanograms per ml. And the reason this is there is really just so people don't have crazy wide unreliability zone, like, I don't know, 0 to 500 nanograms per liter with a cutoff at 250 and 50, no, we sort of want to put a quality limit on the size of the unreliability zone. Okay, all right, so we know how to estimate the size of the unreliability zone, and well, now is the time to estimate the proportion of false results at the edges of this unreliability zone. So this is part of the validation, of course. Okay, so you evaluated your unreliability zone, you decided on the concentrations at which you are going to do your validation for the false results. And so you have one concentration below, one concentration above your threshold. Remember, this threshold, it can be your LOD or it can be a decision point. So you're ready to evaluate the proportion of false results at both of these concentrations. So you spike samples, you analyze them, and at the concentration below your threshold, samples are going to be either true negatives or false positives. And at the higher concentration, samples will be true positives or false negatives. Sweet and simple, right? But how many samples should you spike at each concentration? And the answer to this question is annoyingly a lot of samples, like much more than you would think. And to help you understand why, imagine you have a huge bucket filled with green balls, but there are 5% of red balls that are mixed in. So these are our false results, right? Of course, yeah, green ball, true positives, true negatives, red balls, false results, false negatives, false positives. So if I do a blind draw into this huge bucket, how many balls before I get a red one? Well, on average, it's going to be 20 balls on average, but it might take me much longer than this. In fact, if I want to be 95% certain that at least one red ball will turn up, I need to draw 59 balls. Okay, so for the data nerds out there, the binomial distribution is the engine behind this whole thing. And so I'm sure you see where this is going. If you want to be 95% confident that your method has a 5% false result rate or less, you need to run 59 samples at each concentration. If we had 50% red balls in this bucket, it would be a whole different story. But we're trying to ascertain a small proportion here, right? 5%, 1% maybe. We want to know if the method is performing well. No one is interested in confirming that, oh yeah, my method has less than a 50% false positive rate. Of course not. Mind you, here I didn't even talk about how much you need to get a good estimation of the false results proportion. It would be much, much higher than this. So this is really here the bare minimum that you need to ascertain your false results rate. Okay, so what then is the number of samples that I need to use for validation? Well, it's actually dictated by C and F using this neat little formula here. So N, number of samples in validation, is equal to log of 1 minus C divided by log of 1 minus F. And C here is the desired confidence level. Typically in science, we're going to use 95%, but you can vary it if you want to. So C would be 0.95 for 95%. And F is the desired false results rate. So false positive, false negatives. And let's say here I want a method that has no more than a 1% false positive, false negative rate, then F would be 0.01. And so I calculate my number of samples this way, and I am allowed one failure out of these N samples. Okay, one failure. All right, good, but typically we're not going to use very strange values or values that are different between all of us. I mean, it's not like I'm going to go ahead and have a 97.35 confidence level, right? These are pretty standard usually. And so here's a handy table with some of the most common levels. So if I set my confidence level at 95%, I have different also false results rate that I might be looking for, 10%, 5%, 1%, and I've calculated for you the number of samples. And so you notice that, for example, if I have a 10% desired false result rate, then I need to run 29 samples and I have one accepted failure. What I could do is run double this, so 58 sample, and then I have two accepted failures. Okay, so once I've done my validation this way, I've validated my method at a set false results rate, what can I claim in my reports after my validation? Well, let's take a few examples. If you run 59 negative samples at the lower limit and 59 positive samples at the upper reliability limits, and you get one false positive, one false negative, well, that's good. You've met your one failure criteria, and you can claim method has a false result rate of no more than 5% at the 95% confidence level, right? False results rate being false positive and false negative results rate. Let's say I, again, have those 59 negative samples, but this time I've generated two false positive results. And so, this is over my criteria of one failure. Well, I cannot claim that my method has no more than 5% at the 95% confidence level. Let's start again with these 59 negative sample, 59 positive samples. And let's say I have two false positives and one false negative. Well, I can say that my method has a false positive rate of no more than 10% at the 95% confidence level, and a false negative rate of no more than 5% at the 95% confidence level, right? So it's not mandatory that your false results rate be the same for positive and negative. They can be different. And importantly, a 0% false negative, false positive rate can never be claimed, because to be able to claim that, you would need to analyze an infinite amount of samples, which I'm pretty sure you cannot do. And so this kind of statement is not statistically supported, and you should not use it. Okay, so just to recap, how do we validate false rates of results? First of all, you choose desired C and F values, so confidence level, false results rate level. You calculate the minimum number of samples that you need to analyze to be able to claim those C and F rates. Or you can go by the table. There will be a table with the most common values for CNF in ASBO 36 second edition. And on the slide that I had previously, this was an excerpt basically of that table. So you can use that as well to set your number of samples. And then you analyze n negative samples, n positive samples. And spiked at URL. And for a decision point method, you're going to analyze n samples that are spiked at the lower reliability limit. But for identification method, where the LOD is your threshold or decision point, you're going to analyze n blank samples, and these are going to be your negative samples. And there is a reason behind all of that, but I don't really have the time to get into that today. So yeah, make your lives simpler if you have identification method, just analyze blank samples. And yeah, you check whether you have more failures than your criteria, really. And if a number of failures fit the criteria, then your method is validated for this aspect. Okay, let's do a quick example here, just to illustrate how this would work in a real validation setting. All right, so let's say I have a qualitative LCMSMS method for GHB with a 10 microgram per milliliter threshold. So this is linked to the PERSE in Canada for driving under the influence cases. And for those of you thinking, wow, what a weird example to go after GHB in DUI cases, might I remind you that in my province, we used to find GHB in a good 20% of DUI cases before they arrested the main dealer, and now it's way down. But anyways, so I want to classify my samples as above or below the legal limit. We've developed our sample preparation, our chromatography, and now before we go into validation, we want to estimate our lower and upper limits of reliability. So it's relevant here to have an unreliability zone that's not too wide because we're dealing with DUID cases after all, and so we'll use the calculation approach. That said, we're still conscious of the fact that this is an LCMSMS method, and as such, the sensitivity and size of the unreliability zone, it will vary daily. And so what we'll do is we'll do this estimation over several days, over a 1 month period, and take the worst one. It doesn't ask a lot of us after all. We just run like 5 replicates of the cutoff each time we do a development experiment during this month. And the rest is just calculations. And so we do that, and our worst evaluation throughout this period is 7.2 to 12.8 microgram per milliliter. So let's say 30%, 7 to 13 micrograms per milliliter to make things easier. Okay, good. So let's perform validation at these concentrations. All right, so at the LRL and URL, so 7 and 13 micrograms per milliliter, we evaluate the number of false results. So we spike 60 samples at each concentration, and we obtain only one false positive and one false negative. Awesome. Right, this fits our criteria. Good. We're able to report a method with no more than 5% false results at the 95% confidence level. But of course, remember, we've been quite focused on the false results rate, but there are other elements that we need to check for in a qualitative method. So we look at whether carryover occurs after we inject samples at 1,000 micrograms per ml of GHB. Nothing, this method is carryover free. We do not have any interferences either, nor from the IS, nor from common analytes, or from any of the 10 different matrix sources that we analyzed. Now, instead of estimating the real analog LOD, which is frankly of little importance to us in this context, we use a cutoff as the LOD, and we confirm that all detection and identification criteria are met at this concentration for several days. And this is an LCMSMS method, so we need to consider ionization suppression enhancement. We do this at both the LRL and the URL. If we had significant suppression or enhancement at either concentration, this would jeopardize our false results proportion that we evaluated above, but we did a good job in the development of this method because it seems mostly free from ionization issues, with good averages, good percent RSD. And finally, we want to make sure that we have a bit of leeway for injection, that an instrument doesn't have to be immediately available for injection once we're done extracting our samples. or that, you can have power outages in the building like we have all the time. So we check that processed samples are stable for 24 hours in the fridge, which they are, because the number of false results holds up. So super. All right, awesome. We've got ourselves a validated method. Okay, so I do have a few more notes on this whole thing for sort of particular scenarios that can happen while validating qualitative methods. First, on the types of matrices and sources. So, how many matrix sources or lots should you have in this validation process? And so here ASBO 36 is going to mandate a minimum of 10 matrix sources. You could do, for example, 10 blood sources that are each extracted and analyzed in 6 replicates, right? So mind you, it's not injection replicates, it's really extraction and analysis replicates. And that way you could get to sort of your 59 or 60 number of samples that is mandated for a 5% false result rate at the 95% confidence level. Of course, I mean, in an ideal world, you would use one matrix source per sample, right? So if you had 59 samples to analyze, you'd have 59 different matrix sources. But we do understand that this is a bit non-realistic, especially for postmortem cases, and so that's why we use sort of this workaround to lower the number of matrices required. Okay, well, what happens if I have several matrix types in scope? So what happens if I have urine and vitreous humor and blood, or if I have antemortem and postmortem blood? Well, you can use a single matrix to prepare the decision point, right? So this would be analogous to a calibration curve in solution to quantify analytes in blood, right? So if you want, you can use a single matrix just for the decision point, but the validation, so the rates and the other criteria, they must be evaluated in all the types of matrices that are in scope. So decision point can be in a single matrix if that's what you're going to do in production, that's fine, but you must validate with all of the different types of matrices to prove that it works in the different matrices that are in scope. Okay, what about dual use methods? And here we're targeting specifically methods where quantitative analytes can be turned in qualitative analytes in the event of a QC failure or a calibration curve failure or what have you. Well, for this type of methods, if you intend to allow this in your SOP, your method must also be validated as a qualitative one. So essentially, you must run a quantitative validation, and on top of that, you must make sure that you satisfy all of the criteria for a qualitative method. So this looks like a lot of work when I say it like that, right? It looks like you need to do 2 validations, but really you can reuse a lot of the same data that you use in your quantitative method validation and just repurpose it to prove that it works as a qualitative method in the way that you intend to use it when there is a failure or flip to qualitative. All right. Reporting the results. What we've been discussing this whole time, right? The unreliability zone, the confidence intervals. Doesn't it sound to you strangely like measurement uncertainty? Well, this is not under the ASBO 36 purview. it does make you think about how you report these results, right? Because with quantitative results, you know the drill. You report the number you measured and you report its measurement uncertainty. But what about qualitative results? One option to convey the notion of unreliability, sorry, to the client would be this. Um, any result that falls in the unreliability zone, you report it as likely. It's likely positive, it's likely negative. There's a good enough chance, maybe higher than 5% or higher than 10%, depending on the F value in your validation, that you are in fact handing out an erroneous assessment. So that's all well and good, but can you be more precise? Can you give a number here of like the chance that you're making a mistake or a wrong assessment? Well, you can certainly talk about method performance. So, for example, you could say, okay, bromazole above threshold, right? Analytical method generating no more than 5% false positives or false negative, right? You could say that, um, or you could have something like, oh, bromazole, it's likely above threshold, and then you have a note that states, while bromazole was detected above the method threshold, a higher proportion of false positives, higher than 5%, are expected close to the threshold, or something like that. But as it's quite technical for some of our clients. But the thing is that if you want to go further, if you want to really put a number on the probability that the result for this particular sample is right or wrong, it will be much more complicated. To do that, to talk not in terms of the method as a whole, but in terms of this specific sample, you're going to need to use Bayesian statistics. And do we have another hour in front of us? It it seems like absolutely not, and so we'll leave it at that. But that is what you would use if you wanted a number that's specific to your sample. It's Bayesian statistics is lovely stuff and it's massively interesting, but you sort of need to work your way up to it, and it's certainly not anything that ASB is going to require. Okay, so a few conclusions. This was a lot of new materials to digest, and I just want to recap with some of the most important points. So a second edition of ASB 036 has been drafted and is going to be out for comments at some point. The notion of screening is abandoned in this document. You can still screen, of course, but these methods need to be validated like any other qualitative method. Qualitative methods are to be validated with carryover, interferences, LOD, ionization suppression enhancement, process sample stability. All of this was already in the current ASB version, and the new one, which is the number of false positives and negatives. This is a new requirement of the second edition. In every qualitative method, there is a range around the threshold where results are uncertain. We validate right outside of this zone. The number of false results, false positives, false negatives is evaluated at the lower and upper reliability limits. You might want to acknowledge this unreliability in your reporting, although ASB is not going to force your hand on this just yet. All right, enough of that for now, but if you're interested in learning more, here are some great references we relied on heavily while drafting the second edition of ASB 036. Eurochem CTAC, in particular, well-rounded document covering the basics and more, well-written. This is one of my previous papers where I did explore this framework to validate qualitative methods. And this is a paper by Ellison, which is a favorite of mine in method validation. Really, he's such a good author, really clear papers that are very readable. Just, yeah, I love this author. And something that's upcoming is something that myself, Becky Wagner, and Mark LeBeau have written that is specifically designed to explain uh, what stands behind the modifications that we did in ASB 036 second edition and how it can be applied with specific examples. As Mark would say, this is a work of art or poetry. Um, but yeah, a review paper that is to be submitted to JAT as soon as ASB 036 is published for public comments. I will put a copy of it on ResearchGate and also submit it for publication in JAT. But unfortunately, at this point, since the document isn't public, there's no point in getting this paper out in the public. And as always, if you have any questions, any comments, any need for help, don't hesitate to reach out. So you have my email, and I'm also available on several platforms, and I'll be happy to take any questions just now.